Good evening and welcome back. This is the second video of this kind I'm recording, and if you haven't seen the first one, I highly recommend that you watch that first. It's called Bits and Bytes, and it is intended to be a precursor to this video on files. The idea being that files are essentially just a collection of bytes stored on a hard drive. So in the previous video we worked up from the most fundamental data storage unit, which is the bit, and we went all the way up to bytes and their uses in things like images. The step we kind of skipped in between those is that they do need to be stored somewhere and in some format. You can't just have them arbitrarily lying around. So we organize our bytes on hard disks into files and directories. So what is a hard disk? We broached the topic very briefly in the last video of RAM, which stands for Random Access Memory. And random access memory is a block of storage for bytes that is quite fast to access and is connected to your CPU in some way. The difference between RAM and hard disk drives, HDDs, is that when you turn off your computer, RAM is effectively wiped. So every time you start your machine, RAM will be completely empty, more or less. Hard drives differ in this regard because they persist data, and what we say here is that RAM is volatile, whereas hard disk drives are persistent. That's not to say that hard disks don't occasionally fail, and to some degree RAM is not completely wiped when you turn off your computer. There is some electrical residue, and some forensic techniques are able to be used to recover the contents of RAM after the machine has been powered off, but for all intents and purposes you can assume that when your PC is powered off you lose everything that's in RAM. But if you store something on a hard disk, it should be there the next time that the computer boots up. In principle, these two things are essentially the same in that they are a contiguous series of bytes, and you can visualize them as a grid if you like. This is a little bit more true for RAM than it is for hard disks, because RAM is actually physically laid out as rows and columns, whereas hard disks, traditional spinning hard disks, are circular spinning platters. I'll talk more about that later on. But the more recent solid state drives look more like RAM than they do hard disk drives, but I digress. So in each of these grid items you can store a byte, and then later on you can reference it, although in reality each unit of storage tends to be larger than a byte. In RAM you typically fetch a few hundred bytes at a time when you retrieve data from it. And in traditional spinning hard disks, you retrieve data 512 bytes at a time, and this unit is called a sector of the hard drive. So a sector tends to be 512 bytes. I will admit that I know slightly less about solid-state drives, but I would be surprised if their unit of retrieval is 1 byte. I imagine they will be grouped. And the reason for doing this is usually efficiency. Usually it's usually not efficient to build hardware that retrieves, say, individual bits or individual bytes. It's usually better to fetch larger chunks because the effort required to retrieve the chunk can be quite large. For example, on a traditional spinning hard disk, what you have is a number of platters, and a platter is just a circular disk that can spin, and there'll often be multiple layers. So you'll have multiple disks stacked on top of each other, and there will be an arm with what's called a read head on it that can read the magnetic fields of the various sectors on a hard disk. If you're thinking that this looks a lot like a record player, you are exactly correct. It's very similar in principle to a record player, except that instead of reading kind of the grooves in the disc, it's reading magnetic information. Each bit stored on a hard disk is a very small magnetic field that can be polarized in one of two ways. So why am I telling you this? Mostly because it's interesting. It's good to have a little bit of an idea of the physical layout of things, but the logical abstraction that this provides to us is that we can store what we refer to as contiguous sequences of bytes, and a contiguous sequence of bytes is bytes that are laid out next to each other. So again, we go back to this grid idea. And the hard disk allows us to, let's say that each of these grid cells is a byte. We can store, now this is an awful grid because I've got 1, 2, 3, 4, 5, 6, 7. Just extend this by 1 to make it 8, because we love powers of 2. So if I have a 16-byte file, I know that I can store that in a chunk of 16 bytes on the available hard disk space. And then say I store another file later on that's 8 bytes. I can use another contiguous 8 bytes in the hard drive. And we spoke in the previous video that, let's say our file is just storing some text, and we know that text gets converted into numbers using UTF-8 or ASCII, and those numbers can be converted into bytes, and those bytes get put into the cells in the hard disk. And that's kind of how they get stored. Now, it does get a slight bit more complex than that, because you can't just put bytes on the hard disk at random. Typically, you'll have a file system that manages the space on the hard disk. So if you want a scheme that has folders or directories, the file system is the thing that gives you that structure and decides how to put the data onto the hard disk. And it does all kinds of cool things, like it will give you metadata about the file. For example, when it was created, when it was last accessed. You can even do cool things like only give certain users permission to the file, things like that. And this is all provided to you by a file system. The intricate details of file systems are quite complicated, but in essence, a file system will have let's say we have the whole. So I'm gonna move away from the block idea for the time being, because this needs to be a slightly higher level of abstraction. But in a file system, you'll have something that keeps track of files and the directories that they are in. Oh, I can't spell directories. There we go. And then you'll have a larger section here that is devoted to the file data itself. And typically information about the file, the metadata, the created at, modified at, things like that, will live in the section here. And usually there is some reserved space for admin details that we won't go into. But you'll have entries in here that describe where in this section a file lives. You may have had, or you may have witnessed the scenario where if you're copying one single large file from one place to another, the copy is typically quite fast. You end up getting good throughput. Maybe you'll get many tens or even hundreds of megabytes per second copy speed. But if you try to copy a large number of small files of the same size, it will take much longer. The reason for this is file systems have a much easier job if they have to only allocate space for one large file and one file entry in this metadata store over here, and then just do a big sequential copy, than if they need to find space and do metadata for many, many small files. Because one of the problems that you end up having with a file system, let's do a slightly better diagram here. So let's take a simplified view of the world and let's create a file system. I'm going to go back to our block analogy now. Make sure we draw a table correctly. So in this simplified view of the world, you can only ever create files. You're not allowed to update them, and you're not allowed to delete them. So the first file comes along and it says, I am 4 bytes long. Please allocate me some space on the hard disk and write the file data there. So we're only thinking about the file data section now. We're not thinking about the metadata. So we write these 4 bytes at the beginning because we notice that the beginning has not been written to. And that's that. The next file comes along and it's like, yo, I got an 8-byte file that I want written to the hard drive. So we go, okay, we'll write that in the next 8 bytes. Great. And for good measure, we'll say that we have another 4-byte file. Ooh, that's a highlighter. Didn't mean to press that, but it looks pretty cool, so we'll roll with it. So this is nice and neat and wonderful. And we know that no file's ever going to be deleted, so we don't need to worry about any kind of complex strategies for finding where to put things and stuff like that. But if we remove this simplified world, and all of a sudden we allow people to delete files. Let's say somebody comes along and says, look, this file's just not working for me right now. I'm going to delete it. Ooh, Wow, that's a larger erase than I imagined. So that file is now deleted. But our previous strategy of just using the next block and the next block and the next block will eventually get us to the end. And if we never look back, we'll never see this new space. So let's instead say that we want to use this new space. But the problem now is that this is quite a small chunk of file data space. It's only 4 bytes long, so anything larger than 4 bytes won't fit into there. Worse still, let's say someone comes along and stores a 3-byte file, and we're like, oh, well, it's going to fit in here. 3 bytes. Now, we have this 1 byte left over, and almost no files are 1 byte long. It just doesn't happen very often, so this single byte is destined to go unused for the rest of time. And this is just with a few files. Eventually, if we start storing hundreds, thousands, millions of files, and we're deleting them, and we didn't even mention updating them. If somebody wanted to update this file to be 5 bytes long, it doesn't fit here. So we have a few options. What we can do is we can say, look, okay, the space isn't working out for us. We'll allocate it here instead. So then we copy that data and we add the new updated data on the end of it. And that's fine. That works fine for smaller files, but for bigger files, that copy operation could be quite long. So instead, what you could do is say, I'm going to put one of the new bytes here, and then I'm going to use this over here to store file data. And then in the file metadata, you'll have an additional entry, like a continuation entry that says, this file is actually located in 2 locations in this order. And it starts to get a little bit complicated, but at least you know that you're using your file data space efficiently. The problem is that you'll be end up using more of the file metadata space to keep track of that administratively. So when we end up with lots of spaces that we can't use, let's go back to this 3-byte example we had. This is called fragmentation. It's a common problem in many areas of computing. Efficiently using space is difficult, especially when that space is being changed. If you used computers way back in the 90s, you'll remember disk defragmentation tools. And I remember specifically the Windows 95 one, which gave you this awesome grid layout of your hard disk, and it showed you it moving the blocks in real time. It took hours, but the nerd I am, I'd sit and watch it defragging. I thought it was really cool. We don't typically defrag disks anymore, and one of the reasons behind that is that you shouldn't defrag solid-state drives. Now, why? I mentioned earlier that hard disk drives, with their spinning platters, and they look like record players, and they have a read head, and the disks spin around. If you want to get to a certain place on that disk, you need to wait for the disk to spin so that the read head can get to the right place. And if your file is split over many places on the disk, you'll have to read from 2 possibly very separate locations on the hard disk. Now, this is called seeking, or a disk seek, and you'll see this as a spec or a specification or a statistic listed on spinning hard drives is how long their seek time is. And typically it's less than 10 milliseconds. I think modern spinny disks can get like between 5 and 10 millisecond seek time. But you'll have to pay this seek time if you end up splitting your file data across many different parts of the disk. So sometimes it might not be a good thing to make efficient use of the space on your drive. So fragmentation is not always so terrible. Solid-state drives don't have this limitation though. they are made not using mechanical spinning components. They're made of what's called flash memory. Very, very similar to what you find in USB sticks, or not too dissimilar from what you find in RAM, although there are differences. Now, solid-state drives have a very separate problem. Let me redraw this grid because it's going to be a little bit messy. So you can still think of this grid system for solid-state drives, and it's actually a lot more accurate than it is for spinning drives. Because I think, I could be wrong, but I think that flash memory operates in a grid system. So the great thing about flash memory is there's no seek time. You don't have to worry too much about seeking. There is definitely a latency for accessing a specific cell. It does take time. It's just significantly less than the 5 to 10 milliseconds that you have to pay on a spinning disk drive. But because there's no mechanical read head that you have to wait for, if you miss your part of the disk that you want to read, you have to wait for it to spin back around again. There's nothing quite like that for a solid-state drive. So it can do what's called random access quite well, which is something that spinning disk drives are very, very bad at. But spinning disk drives are really good at sequential access. Because once you start reading from one part of the disk, the data is typically laid out in a way that as it rotates, you get data sequentially. I'm going to have to draw a diagram. I don't quite know how to get new pages in this, but what I'll do is I'll just draw it kind of small over here. So on spinning disks, you typically get the data laid out in rings, and each ring is a sequential part of the grid, let's say. So once you start reading from one part of the ring, going around is reading sequentially laid out bits of memory on the disk. So that's why spinning disks are quite good with sequential access. And logically, you can see why they might not be so good with random access. Excuse me, I'm going to take a small drink here. So the problem unique to solid-state drives that is not immediately obvious is each cell can only be read from and written to a limited number of times. So let's say each cell can be read from or written to 10 times. So you could do 5 reads and 5 writes, and that would be it. It would then stop being functional. Or you could do 8 writes and 2 reads, and it would stop being functional. This leads to some interesting consequences. If we prioritized filling up early cells, as we did previously with our hard drive example, we would find those cells would die much quicker than the rest of them. So that's why solid-state drives typically do something called write balancing, and they will, when new data comes along, they will try and use cells that are less used overall than others, in order to preserve the lifetime of the disk. Now, in reality, I think the numbers are something like each cell can be written to or read from 1 million or more times. Like, it's a large number. It's unlikely that you'll hit that number very soon. I believe the lifetime of solid-state drives, provided you aren't doing anything specialized or very stressful, will be longer than that of the spinning disk drives, in part because there are no mechanical parts, but the limiting factor is the degradation of cells as you use them. So what does this have to do with defragmentation? Well, defragmentation is very stressful on the hard disk. if we go back roughly to our previous example, and we say we have some files kind of fragmented all over the place. So we have the 4-byte red file over here. Let's introduce a new blue file that's split kind of awkwardly, and then a third file just for a bit of fun. Let's fill up a few more bytes with this grey file. Ideally, you want to have data that's related close together in a contiguous format. So you'd want all 4 of these red cells up at the top here, followed by 5 of the blue cells and then the grey cells, because sequential access, I think even on solid state drives, sequential access is faster than random access. And this is due to a concept we'll go into in some more detail after I've gone through this example, which it's called locality, and I think it's fascinating for now. Let's say you rejigged all of this so that you could get faster sequential access. Now, the problem is you have to move almost all of this data in order to get the result that you want. You have to remember that you can't just swap 2 cells. That doesn't work. What you have to do first is you'd need to... Actually, probably what you would end up doing if you were writing a defragmentation algorithm is you would pick a whole new area. Let's say we start again down here, and I say, I'll take the 5 blue ones first, and we write them out to here in order. Then, once we're done with that, we delete them from where they were. Then we decide to take the red cells, and we write those out in order. Now just imagine this is left to right, top to bottom. So this little dude in the bottom left is actually contiguous with these up here because it's left to right, top to bottom. And once we're done with that, we can delete those from up here. I'll rebuild my grid slightly. It's kind of getting a bit ruined here. Then the last thing that we do is we take all the grey cells and we write them down here. 7, yeah, thought so. Great, and then we delete them from here. So instead of... So why do we do it like that? We do it like that because it reduces the number of operations. You might be thinking, why don't you just keep everything up in the top left? That was neat and tidy, I like that. Why you gotta ruin things, dude? But if I want to keep everything up in the top left, it involves like double the operations because you have to copy everything back now. It's much better to defrag into a new space. And if you're like me and you used to watch the Windows 95 defrag tool, you would have noticed that it does this, right? It chooses a new space for this data, defrags it into a completely new area to kind of reduce the number of operations that need to be done. And that's how defragmentation works, but you don't want to do it in solid state drives because it's really stressful. You end up degrading your cells and you hit the read-write limit much higher. That's much quicker than you would if you don't defrag, and the benefit of sequential access over random access on a solid state drive is not that big, certainly not compared to a spinning hard disk. So defragmentation I think it's mostly a thing of the past. Modern file systems do a good job of avoiding fragmentation, and modern hard disks don't benefit quite as much from defragmentation as older hard disks did. There's one small detail in this diagram that I did specifically wrong that I'm just going to quickly go over before we start talking about locality, and that was the data up here got deleted, right? So we deleted what was in all of these cells after we defragmented it. The reality is that that wouldn't happen, and it wouldn't happen because a delete is actually just a write, right? when we say that we delete data, all we're doing is we are writing 0 into each of the cells. 0 representing like an empty value. Typically hard disks don't do that because it's another operation. You don't need to. All you need to do to delete a file typically is to delete the metadata entry for it in the metadata space that we discussed earlier. You don't need to go ahead and write over the disk. Some applications do this. If you want to really make sure something's deleted, you on a, say an old magnetic hard disk drive, you actually have to write random data onto that disk space many times in order to get rid of any magnetic residue. If you just wrote zeros, the kind of leftover magnetic force would reveal what data was there if you forensically tried to recover the drive. So typically what they will do is a few dozen times they just write completely random data over where the data was, and then possibly zero out. I don't know. But for a lot of things you just don't need to do that, right? And it can be kind of useful not doing that. So there are a whole bunch of file recovery programs that exist, and the main thing they do is they just scan bits of the hard drive that the file metadata claims isn't used, and they just see what data they find. So let's say you store an image on your hard disk. One of the things about image files, and a lot of different files for that matter, is that they look like image files. When you go and you read the binary data, image files, and again most other files, typically start with a predictable, what's called magic number at the start of them. And I can't remember what the magic number is for JPEG files off the top of my head, but they will usually have something at the very beginning of the file that identifies what kind of file they are. So these file recovery programs will just scan through parts of the disk that the disk says aren't claimed by anything to see if there's any leftover data. And this can be really useful. Like if you've accidentally deleted a photo and you desperately want to recover it, this could really come in handy. And it's why people say if you have deleted a whole bunch of data accidentally and you want to recover it, you need to turn off your machine ASAP, because you never know what's happening on the hard disk. Things are reading and writing the hard disk all the time. The longer you leave it on, the more likely it is that that space that your image used to live in gets overwritten, at which point it becomes very difficult to recover. Cool, okay, so I have promised I would talk about locality. Now, this is, it's a bit squeaky than I imagined. Locality is one of my favourite concepts, and it's a very computer science-y concept, but I'm going to try and present it as kind of practically as I can. Like, there's a lot of theory behind locality, but I think the reality of it is that it's really quite a simple concept. So there are two major types of locality. So let's put locality up here. So you have spatial and temporal. And these two things are foundational in computers. Almost everything takes advantage of these spatial and temporal localities. So spatial locality says that if you access a cell of data on your hard disk or in RAM, it is very likely that the next data you want is in close proximity to that data. So if you read a cell, very, very likely that you're going to want the next cell, and then the next cell, and then the next cell, and so on and so forth. So data close by is usually related, and it's usually wanted in kind of like quick succession, right? Which leads us to temporal locality. And temporal locality says data you have accessed recently, you probably will want to access again very soon. So if you have a file open, it's likely that you're gonna, say you have a directory open, actually better example, you have a directory open. There's probably a small set of directories on your PC that you open quite regularly. So that data is related, and it's often accessed together, and it's often accessed frequently. So why is this so foundational? So computers have become blazingly fast, like faster than anyone a few decades ago could have comprehended. We are carrying around in our pockets more computing power than the entire world had at its disposal just a handful of decades ago. The common example that gets put out there is that modern iPhones have significantly more computing power than the original moonlanders, and it's quite amazing to think about. Like, just stop and give it some thought. The implications of that are just incredible. But I digress. So why is this so foundational? It's foundational because it makes computers extremely quick. I should have researched this before I began the video, but computers typically operate in hierarchy. So your hard disk, so let's say this is a hard disk space, is usually quite large, but it's quite slow. Then you have RAM, and RAM is usually a lot smaller than the hard disk. It's a lot faster though, and it's connected to the CPU, so it is special in that regard. I've said that twice now, and it's not technically true. It's not connected to the CPU, but there is a data bus by which the CPU can get things out of RAM, so that there is a connection between them, but it's not necessarily direct. It goes through another few components before it gets to the CPU. The principle is that they are kind of connected. But kind of after RAM, we have a whole set of much smaller memory called caches. And these only exist because spatial and temporal locality are phenomenal predictors of what you will access and when. You may be thinking on the scale of files and things like that, but I think to really appreciate this, it's worth thinking on a much smaller scale. These are not really to scale. Hard disks are many times bigger than RAM. It's not unusual now to get terabytes of storage in a hard disk, whereas RAM on like modern systems you get between 16 and 32 gigabytes. Caches though are measured in, I think the bigger caches are like 32 megabytes, but they're actually, so there's even a hierarchy among caches. So you usually get different what are called levels of cache. The biggest levels being maybe 32 megabytes, the smallest levels being just a few hundred bytes. The differentiator is how close they are to the CPU and how quick they are to access. So at every single stage, you get much faster access, whereas reading from a cache can take a handful of nanoseconds, whereas reading from RAM can take a few hundred nanoseconds. And reading from a hard disk can take milliseconds. So there are huge scales at play here. But say you open an image file. One of the things that you typically do is you'll sequentially read from the hard disk. And you'll read in blocks of like 512 bytes, maybe a few kilobytes, depends on the hard disk. And you'll read that into RAM, and then it'll end up somehow in the cache, and then it'll end up on the screen. But spatial locality is very much at play when you load an image in from disk, because file systems and operating systems will really try their best to lay out files contiguously and sequentially. Sorry, that's kind of redundant. They'll try and lay them out contiguously so that the bytes are all next to each other and they're not fragmented. So that is a great example of spatial locality. A good example of temporal locality, give me a moment to think. It comes up a lot in programming. In programming, you can kind of load bits of data into your program, and there are pieces of data that you end up using a lot. For example, if you had a a list of things. Could be anything, right? Let's just say that each of these cells is itself a number, and this list of number represents the birth year of a bunch of your friends, maybe. If you wanted to get an average, when you write a program, you would initialize a variable called sum and a variable called count, let's say. And for each of these cells, you would add the value onto sum, and as you go through, you'll increment count for each element. Sum and count display really strong temporal locality because you've added to sum recently and you've increased count recently, and you'll end up doing it 8 times. So in this example, we see both spatial and temporal locality at play. And when you load data in from the disk or from RAM, anything you access, let's say you express interest in reading this from memory, what will happen is it will actually load in this whole thing from memory into a cache, because it says, because you want this one, odds are pretty good that you want the rest of it as well. So doing this whole sum and count will only usually require one read from RAM into cache, and then from there, instead of doing a 100 nanosecond round trip every time you want to get the next thing, the computer's already preloaded it into this bit of memory, this cache down here, that can be accessed in 3 or 4 nanoseconds. So you end up saving huge amounts of time because of spatial and temporal locality. I feel like I've rambled way past the initial topic, which was files. I think I may end up renaming this video to storage, because these are all different types and different hierarchies of storage. But I think I'm going to put this video to bed. Thank you so much for joining me. I realised we covered quite a lot of ground, and I'm extremely happy to answer questions in the comment section, so don't be shy, feel free to ask anything. If you have ideas on where this series should go, there are things that you're confused about, if you don't think the videos link together well, if you feel like going from bits and bytes to this video is a big jump, and you think I've missed out some detail, I'm happy to fill that detail in. The goal here is to create a set of videos that all build on each other. So for every video you can say, to understand this video, all you need to do is to understand these previous videos, and you should have enough material to get what I'm talking about. So that's the idea. I want to build up this series that builds on itself from the fundamentals all the way up to the more complex things about how computers work. But there, thank you again for joining me, and I will see you all very soon.